Welcome to Lecture 25C entitled Vectors and Coordinate Transformations. And this material comes from Reading Assignment 0, Sections 4, 5, and 8 and 9, 8 being problems and 8, 9 being solutions. So the objectives here are to gain familiarity with manipulating vector field equations for physical problems. And this can be basically in different coordinate systems, specifically cylindrical and spherical coordinates. Second is the properties and the manipulation of vectors in other coordinates. Thirdly, coordinate and vector component transformations, and in particular an example which we'll look at, which is question 4 from chapter 8 of the document. The relationship between unit vectors in different coordinate systems, and finally different differential geometric entities in other coordinates. So the basic concept visualization skills is basically feeling comfortable with doing coordinate transformations. And the items below, note 1, note 2, note 3, are just some additional material which you might find useful. All right, this is the outline. It's just typical in terms of what is to provide. It's going to be provided. These are 5 different items. Leave it up to the person reading it just to go through and see for themselves what is to follow.
Right, so at this point, we're basically going to look a little bit more in terms of how to decide on what the basis vectors and other coordinates should look like. And so our starting point basically is to determine a position, to work with position vectors. Sometimes it's mathematically more convenient to work in a coordinate system other than a Cartesian coordinate system. The reason is that just things are simpler. And also, we're invoking symmetry. We're using this symmetry and then basically simplifying the problem. So the quantities of interest that we're interested in setting up the problem are the position vector, which sweeps out point on a line. So for instance, the vector in blue is a position vector. And this position vector is evolving. With t could be time, but it could also be just a parameterization variable. So this is the position vector at t, and this is the position vector at t plus delta t. This diagram on the right shows basically a finer detail. There are small steps showing how the tip of this position vector traces out a particular contour. All right, so what we're interested in is the tangent, basically, to this line, which is being swept out by this position vector, right? And the direction which we sweep along the line, we can look at as having tangent vector at each point along this line. So our interest is to determine what the tangent vector is, because it will allow us to establish basis vectors when we deal with other coordinates. Okay, so the tangent vector we can basically determine relatively simply. If we take the difference between this vector and this vector, then we basically establish this vector, which in this diagram is PQ. It's called delta R, which is just RT plus delta T minus R of T. All right, so that's basically what we see here. And now we just do a little trick. If we divide this expression through by delta T, which is what we've done here, and then multiply through by delta t, which is what we've done here, then this expression is exactly the same as the original expression that we started with. So this numerator term is actually delta r, which is the delta r that you see here. All right, so now what we do is a limiting process. This length we call arc length, right? A differential arc length is basically what we're going to be interested in as we make this delta t become vanishingly small. So ds or dr would be a limiting process where we let delta t go to 0 of the expression delta r over delta t times delta t, right? And the limiting process basically allows us to show this as being nothing more than the derivative of the position vector with respect to this parameterization variable t, dt. Now this can also be written in this form, which is r prime dt, or sometimes it's written as r dot dt. The dot basically infers a derivative, and it's with respect to time. So this that you see here is nothing more than this red vector that you see here, which is the tangent to the contour at a given point in time. In this case, it would be the tangent at point P. So this is what we're going to be using quite often. So any given line will have a tangent vector, and the derivation of that tangent vector will follow along the lines of the expression that you see here. All right, so let's look here now at how we're going to go about working with vectors and other coordinate systems. So the example I've given here is a two-dimensional problem because it's easier to visualize. And the example is r of theta is a doublet, consists of two coordinate parameters, r and theta, in 2D. And what we'd like to do is to determine the two basis vectors, all right? One dealing with in the direction of r and one dealing with in the direction of theta. So on this diagram on the right, which you can access at that URL, the vector that's shown as yellow, it's an orangey yellow, is a position vector pointing to an arbitrary point on the xy plane. And it takes on the form rxy, but x is a function of r and theta, and y is a function of r and theta. So that basically is shown in the bracket there, fr theta, gr theta. The red vector that you see is a position vector tracing out a line holding the value of theta fixed, and it would take on the form r subscript r, x subscript r, y subscript r. Again, it will be a function f of r theta, but in this case, since theta is held fixed, theta naught represents a fixed value of theta. Similarly, gr theta subscript 0, theta naught represents the constant value of theta. The position vector tracing out a line holding r fixed, which is the one in blue, would take on the form r subscript theta. And in this case, basically, r is held fixed at r equals r naught. So let's just review then quickly. So there's the position vector, blue, and this blue line is going to sweep out along this direction. The red is this one here, and it sweeps along the radial direction. The y hat is just at this location, is the basis vector in the xy plane, and this is the x hat, which is the basis vector along the x directions. And this point here is either xy, but also in polar coordinates, we would call this position r naught and theta naught. Okay, so we want the basis vectors at this location, but in this new coordinate system. So we know that one will be pointing along here, and one will be pointing along here. The one pointing along here would be a tangent line, and this tangent line would be holding r fixed. Here's another one. This is the red one, right? Turns out that the black lines, the black arrows represent the unit vectors, or basis vectors in this new coordinate system. In this case, it would be along this line here, okay? All right, so the basis vector along the line holding theta fixed and evaluated at some point r naught, which is right at this location, would be dr by dr, right? And you're evaluating it at the point of interest, which is r subscript 0, theta subscript 0, dr. Okay? And so this would be in the r direction, so it would be some scalar multiple of r hat. But you can also write that as some linear combination of the x hat and y hat vectors. So either this direction was r hat, or as some combination of x and y would give you the same vector. The basis vector along the curve holding r fixed and evaluated at some point theta naught would be just taking dr with respect to theta, okay? And so this is the one that looks at a vector that's pointing in this direction, right? So in this case, basically, you're going to evaluate this at the position r sub 0, theta sub 0, and the differential lengths would be, as shown, d theta. And so this is in the theta hat direction, and it would be take on some value, so we've got a scalar value b there. And again, it can also be represented in Cartesian coordinate system based on a linear combination of x hat and y hat, and that's shown there. So they're equivalent to each other. So again, a, b, c, d, e, and f are scalar constants. And by the way, the nomenclature, this d we'll be introducing a little bit later. It's called a partial derivative. Why? Because when you look at the function, it has r and a theta, and so we can take a derivative with respect to r or a derivative with respect to theta. And so the fact that we have options in terms of what we can take derivatives of means that we use the notation of partial derivative. All right, so if you want to take a look at the simulation of this, the interactive simulation, just look at the URL here. And again, slider t, and you'll see this come up. You've got a slider for p and slider to t. Basically, it's a position vector for r. And so it basically tracks along this line here. And for p, it tracks along this red line here. The tangent vectors are the ones that are in black here. This should actually be right over here, but it would basically collide with all the other stuff. And this should also be closer in, but it would collide. So these are basically the tangent vector. Black tangent to the radial line, black tangent to the circumferential line. And the Cartesian orthonormal basis vector, orange vectors. Okay, so that's this one here and this one here. All right, so now let's talk about properties and manipulation of vectors and other coordinates, some specific details which are really important to understand, because this is where so often we all go wrong. I mean, forget about the fact that there are conventions. Okay, so let's start with the first point, that the direction of the basis vectors in the new coordinate system, if not Cartesian, meaning curvilinear, will depend on the position in physical space. That's going to be a given. A vector at a given position space in any coordinate system is a linear combination of the orthonormal basis vectors for the respective coordinate system at that position in space. Again, we're only going to basically make use of orthonormal basis vectors in this course. So in the new coordinate system, we'll find these vectors are orthonormal to each other, and thus the transformation matrix M, to be defined soon, we're getting there, is an orthonormal matrix, and that means that it has a specific property. That property is that the inverse of the matrix is equivalent to the transpose of the matrix. That makes life a lot easier because it's a simple manipulation to go from one form to another. And the main point I want to drive home that coordinate systems used are all right-handed. And so what does that mean? It means the ordering of vector components x, y, z, or position components x, y, z. One is in parentheses, the other one is in angled brackets. And labeling of coordinate axes follows set rules in an order to ensure right-handedness. So if you look at the picture on the left, I mean, that's a right hand. It shows basically the direction of A, the direction of B, and the resultant direction of A cross B. If we took A to be the x hat vector, B the y hat vector, then A cross B would be the z hat vector. That is what we mean by right-handed. Okay, so always perform that operation. The ordering sequence of the tuplets or tuplets, x, y, z, or y, z, x, or z, x, y are all right-handed. So there's a sequence here. And so you would see that going from here to here was more like a shift. So what we're doing here is to shift x to the right, wrap around and bring it back on the right. That means y moves over one, z moves over one, x moves to the end. If you shift one more, then z goes here, x goes here, and y comes around to the other side. So any combination of this form is a right-handed system. If on the other hand, if I took any of these two and interchange, then I'm dealing with a left-handed system. Keep that in mind. So what about basis vectors for other coordinate systems? In polar coordinates, the basis vectors are r hat, theta hat. Cylindrical will be r hat, theta hat, z hat. And spherical is rho hat, phi hat, and theta hat. All right, if it's a right-handed system, you'll see there's a particular pattern here. You have r, then followed by theta. Of course, I'm showing a question mark here because in polar coordinates, basically, there is no third dimension. But we essentially can invoke it by essentially saying it's more or less similar to a cylindrical coordinate system. And so this is always theta is taken to be essentially in a counterclockwise direction in the xy plane. All right, here it's clear. I mean, this is r theta followed by z. All right, so you can look at this ordering. right? If you used your right hand, you'd find that r hat, theta hat would produce z hat, right? And you'd have a right-handed system. Spherical would involve rho hat, phi hat, theta hat. And again, the ordering is important. Just a quick reminder, the direction of the angle phi is measured with respect to the z-axis in spherical coordinates. And the direction of angle theta is taken in a counterclockwise direction in the xy plane. And now comes the big warning, because every year we run into this difficulty, that the moment you take a course in the spring term electromagnetics, they use different symbols and everybody gets confused. So just a reminder, some textbooks reverse the roles of psi and theta in spherical coordinates. But the following is always true. The second element in the tuple, okay? So that would mean this guy. Forget about the label. 1, 2, 3. Second one. The second always refers to the angle measurement with respect to the z-axis. Period. Full stop. And the third element in the tuple refers to the angle measurement in the xy plane. So the third one, doesn't matter what the label is, refers to the angle measurement in the xy plane. Keep this in mind. I know it may be easy to forget, but it's going to hit you next term, so just be reminded of it. All right, so let's now figure out what these transformations are. I'm going to start with a simple illustration which is based on a geometrical approach, which is possible to do in 2D, but becomes just a little bit unwieldy in higher dimensions. And so then we will basically just use vector notation to effectively do the same thing. So what I've done is shown here a number of pictures. If you look here, this is just basically showing in 2D the coordinate system. So here is a position vector, a length r, right? If you want to know what the x is, it's a projection, so that would be r cos theta, and this would be r sine theta. So x equals r cosine, y equals r sine theta. And the limits on r are greater than 0 and theta from 0 to 2 pi, so you can map out the full xy plane. All right, then we have basically the basis vectors. Remember, in a polar coordinate system, we essentially had a line which is radial and a circumferential line at a given radius. This is a given line at a given theta, a line at a given theta. All right, and the intersection between these 2 points is of these 2 lines is this given point right here. So the basis vector here would be pointing this way, that's theta hat, and the basis vector here is the one r hat pointing in this direction. Okay, as far as the Cartesian vectors, y hat would be pointing here and x hat would be pointing in this direction. Now, if I took an arbitrary vector at this location, any direction you want, then what is clear that I can represent that arbitrary vector in Cartesian coordinates or polar coordinates. It's the same vector. So these two essentially are equal to each other, except I've used different basis vectors here compared to here. All right, so the two are equivalent to each other. Again, we're using a right-handed coordinate system. Hence, theta hat is pointing in a counterclockwise direction. Okay. All right, so now comes the business of how do we transform from one system to the other. So let's start. We know that these two are equivalent to each other, so we can equate those two. All right, so I'm going to take Vx. I want to know what Vx is. Well, I could get Vx basically if I took the dot product of the left-hand side and the right-hand side. So V Cartesian dot x hat would be equal Vx x hat dot x hat. X hat dot x hat is 1, so it would give you Vx. But y hat with an x hat, their orthogonal, gives you 0. All right. Alternatively, I could take this one and dot product with x hat. Perform the same calculation. Of course, it'll look different. So that's precisely what I've done. That x hat here is just this whole entity, dot x hat. So you just take the dot product of this and the dot product of this, and you end up here with, this as being dot x hat. You can also figure out what Vy is. If you took the dot product of y hat with this, equivalent to taking the dot product y hat with this, then you end up basically with Vr at V theta theta hat dot y hat. And so now what we do basically is write this in matrix form, Vx, Vy, right? And we have a column vector here, Vr and V theta that we create. So you basically just rearrange these things and you'll find that the matrix elements have r dot x hat, theta hat x hat, r hat y hat, and theta hat y hat. All right? If you do r hat dot x hat, you get cos theta. And similarly, you can figure out what these are as shown here. And where do we get that information from? We go to this diagram up here. So if you look, for instance, just for example, r hat dot x hat. Well, r hat would be pointing in this direction. X hat would be pointing in this direction. So if I took the dot product between x hat and r hat, that's just the angle, cosine of the angle between the two. It's a projection. If I look at, for example, the term theta hat and x hat, theta hat's pointing this direction, x hat's pointing in this direction. All right, and you can look at the various angles and realize that you're going to end up with basically a trigonometric expression after simplification, which just says that's minus sine theta. So you group these two all together. We know what these terms are. These are the terms that you see here. Put them together, and this now becomes the M matrix. Okay, these are the values of the M matrix. All right, now because we said these as an orthonormal or a matrix, that means that if we would like, for instance, instead of understanding what Vx, Vy is a function of Vr over V theta, then we just have to multiply both sides by the inverse, but the inverse is equivalent to the transpose. So if we want Vr V theta given Vx, Vy, then it would just be M transpose times the column vector Vx, Vy. And so the transpose would mean take this row and make it into a column, and take this row and make it to the second column, which is what you see here. All right, just again, what M is an orthonormal matrix. Well, what does it really mean? That matrix rows and matrix columns are orthogonal vectors, and each vector is a unit vector. So for example, here, if you took the two column vectors, okay, and take their dot product, okay, if they're orthogonal, they should be 0. Well, sure enough, they are. Okay, if you take instead two row vectors and take their dot product, you get 0. If you take any vector and determine what its magnitude is, it'd be cos squared plus sine squared, which is just 1. So magnitude is 1, and vectors are orthogonal. So that's why we call it an orthonormal matrix. Okay, so now that we've basically looked at how you can visualize a transformation matrix using a geometric approach, we'll do it more in terms of an approach using just plain linear algebra. All right, so let's look at the same problem redone. So the transformation is x equals r cos theta, y equals r sine theta. Again, there are limits on r and limits on theta. So that basically maps out the xy domain. The position vector would be x hat plus y hat. But in polar coordinates, that would just be r hat. That's basically the equivalent position vector in polar coordinates. No mention of theta here, by the way. All right, what is the vectors in the direction of the new basis vectors going to be? Well, you have to take the tangent vector, which means you take dr. Okay, so this vector, dr by dr, is in the direction of the tangent vector. So that means basically you have to take the derivative of this with respect to r, but x is given in terms of r here, and y is given in terms of r here. So if you take the derivative, you'll get this expression here. Similarly, if you want dr by d theta, you have to take the derivative of this and this with respect to theta, and you end up with this expression here. All right, what we want are basically unity vectors. They're going to be orthogonal to each other, but we'll call them orthonormal basis vectors. So you have to take the individual vectors and multiply the magnitude of the vector, which is what I've done here. So you take this vector, divide it by its norm, and you'll end up with this term here. Similarly, if you take this vector and divide it by its norm, and you end up with this vector here. All right, again, because of basis vector invariance, we can either write some arbitrary vector of that position as Vx x hat plus Vy y hat, or we can say that it's Vr r hat plus a V theta hat. Okay? All right, so we know, though, that r hat, from this expression, we have it. So we can substitute here. We know we have theta hat, so we can substitute here. And now what we want to do is rearrange these two so that everything has either got x hat or y hat. And so this is what I've done here. Here's the x, all the terms grouped with x hat, all the terms grouped with y hat. All right, and so we have now an expression for Vx, all right, and we have an expression for Vy. We can put that in matrix form, And if you do that, you'll find you'll end up with this expression, which is essentially the same as what we did on the previous slide. Okay, so more or less this is the approach we would normally take. All right, so now let's look at cylindrical coordinates. All right, so the transformation for cylindrical coordinates is here, the inverse is here. The position vector in this case would be an r component along the azimuthal plane and a z component in the z direction. Vectors in the direction of the new basis vectors, again, these are the tangent vectors. Okay, so we take dr by dr, and dr by d theta, and dr by dz, and we compute them, which is what I've done here. But we want the orthonormal basis vectors, which means I have to divide each vector by its norm, which is what I've done. So that's the line that you see here. All right, so you compute that, and now you have the basis vectors in the new coordinate system. And again, we go through the same process before. For an arbitrary vector at a given position, you can either represent in the basis vectors for Cartesian form or in cylindrical form. And so this is the equivalent of the r hat vector, which you get from here. And this is the theta hat, which you get from here. And the z hat vector basically is 1, so no change. Then you regroup this so that everything now is in terms of x hat, y hat, and z hat. And then you put that in matrix form where you now have a Vx, Vy, and a Vz component, Vr, V theta, Vz, and you end up basically with this being the M matrix. If you want, on the other hand, to put Vr, V theta, Vz in terms of Vx, Vy, Vz, then you just basically multiply through by the transpose matrix. So that's how you would handle things in cylindrical coordinate system. Again, the picture representing the different surfaces intersecting, which we discussed in the previous lecture, they're right here. All right, so for spherical coordinates, here's the transformation. This is the inverse, and the position vector is just going to be rho hat. All right. All right, so what are going to be the vectors in the direction of the new basis vectors? Dr d rho, dr d phi, and dr d theta. All right, so all you're doing basically is to take the x values, the y values, and the z values, take the derivatives with respect to rho, r, and theta, and that basically gives you the vectors in the new coordinate system. But we want unit vectors, so you have to divide by the norm, which is what we've done on this side here. So this is divided by the norm. So this is going to be your rho hat vector, this is the phi hat vector, and this is the theta hat vector. All right, so again, basis vector invariance. You can write it either in terms of the new basis vector or the old basis vectors. So this is the rho hat vector, this is the phi hat vector, and this is the z vector from the previous page. All right, and so now we equate, first regrouping things so that everything here is grouped in terms of x hat, y hat, and z hat. And then write everything out in matrix form, which is what I've shown here. And we end up with a matrix here, which now is M. Or if we want to invert, which means express V rho psi theta in terms of x, y, and z, then that just becomes the transpose of that matrix. So that more or less gives us the process for coming up with the transformation matrices. All right, so let's go through an example, which is question 4 from chapter 8. All right, just in red, cannot add or subtract position vectors in a non-Cartesian coordinate system. Why? Because the orientation of the vectors will be changing depending on where you are. So we can't do it. So what do? Well, we have to transform the vectors into Cartesian coordinate reference frame first. Okay, we know how to do that because we have the transformation matrices. Then we can add, subtract the vectors in the Cartesian coordinate reference frame. And finally, if we transform the final vector back to the desired coordinate reference frame at a given position, if it's required. So let's take the example. Consider the points P, written in cylindrical coordinates. So R is 3, angle theta is 30, and Z is 1. And another point which has radius 0.1, theta 90, and Z equals 2. P superscript T doesn't mean transpose. It's just a label that we've used for this example. So part A asks you to find the distance between P and PT. using row vector notation and assume the column vector is r equals ppt. And the second part is determine the column vector r equals ppt at positions p and pt in cylindrical coordinates. So the diagram on the right there is 3D. It can be accessed at that URL, which is down here. And just so for reference sakes, everything is color-coded. So over here, blue vectors are the position vectors for P and PT in Cartesian coordinate systems. And the vector r Cartesian is ppt, which is the vector between the points P and PT. The purple vectors are scaled versions of the vector r cart at location P and PT. Scale just meaning made small enough so that basically it stays within the size of the page. The black dots are the different points, but we're labeling here in cylindrical coordinates, so they're given an r component, a theta component, and a z component. The red circles are of constant radius, one at r equals 1 and r equals 3. That corresponds to the actual 2 points that we were considering. The black vectors are lines in the direction of constant azimuthal angle theta, and turns out to basically be in the direction of the basis vector r hat. The red vectors are in the direction of the basis vector theta hat, and the green vectors are projection of the purple vectors onto the xy plane. Okay? Anyways, feel free to look at this interactive simulation so you get a better handle on the geometry of the problem. Okay, so let's go through the problem now. So first of all, I'll restate the problem here. Consider the two different points. And so then the question is, find the distance between P and B2 using row vector notation and assume the column vector is r equals ppt. Secondly, determine the column vector r ppt at positions P and PT in cylindrical coordinates. So solution to part A is to transform points P and PT into Cartesian coordinates using the transformation for cylindrical coordinates. So x equals r cos theta, y equals r sine theta, z equals z. And so we can just basically, we know what the r value is, the theta value is, so we can transform both of those into Cartesian coordinates. So there they are. There's for P, and there's for PT. And then compute the magnitude of the vector r of t, a row vector. All right, so these are already in row vector form. So the vector r of t would be just to 0, 1, 2 minus 2.6, 1.5, and 1. All right, so that's a difference between those two vectors that we've chosen. All right, so we have 0, 1, 2 here, and this one here. So this is RT. And if you do that, you get this value, and that's just going to have an RX, RY, and RZ component. The magnitude you can compute, it's just the norm, and that just turns out to be 2.83. Okay, so just a general comment. We can move interchangeably between a row or column vector representation just by taking transpose. The magnitude of the vector is independent of the choice of column or row representation. That's either magnitude of R or magnitude of R transpose. And we can use a vector dot product or matrix product convention to compute the square of the magnitude. So rt dot rt would be a row vector and a row vector dot product. That's equivalent to taking a row vector times a column vector, right, in matrix form. So this is not a dot, this is a multiplication, right? Or you can take its transpose, okay? And that's going to give you a case of scalar. This is a scalar, they're equivalent to each other. So you're free to use dot product convention or the matrix convention, just recognizing what the rules are. Okay, so let's carry on. Part B, column vector R in cylindrical coordinates at a given location. Well, let's figure out what the transformation is. We want basically cylindrical coordinates. So we're given Rx, Ry, Z. We want R theta, Z, which means this is now the transpose of the transformation matrix. All right, we know what is in cylindrical coordinates, so I've just written it here. And so all you need to do is plug in what the value is theta is at a given position. And so that's precisely what's being done here. All right, we've got this vector, which is the R vector in Cartesian. This is at a given position, and we end up with this. Okay. For the other one, we get the same R vector in Cartesian, but a different location, and we get this. All right, so this is the vector that you get. If we look at just the projection, which means we only look at what's on the XY plane, then we don't worry about the ones. and we just write it as shown here. So this is easier to visualize now. Okay, so you'll notice here, for instance, there's RT projected, which is green. All right, so if you look here carefully, if I wanted to basically express this green vector in terms of the basis vectors x hat and y hat versus here, essentially it would be looking at the same problem. Okay, but when we're dealing with cylindrical coordinates, the theta hat here is pointing in this direction, r hat's pointing in this direction, and green is pointing this way. That's quite different than the picture you see here, where now the red's pointing here and the black is pointing here. So clearly, you need the transformation matrix to make sure that you account for the fact that the position of the basis vectors are position dependent. All right, so just to wrap up, there are just a couple things of interest. The relationship between unit vectors and different coordinate systems. I've just basically written them down here: polar coordinates, cylindrical coordinates, and spherical coordinates. You can make reference to them if you wish in future when we start dealing with this towards the end of the course.
All right, so the last slide I'd like to consider is this one here, which is more of a summary slide. You'll find this very useful for the course going forward. These are differential geometric entities in other coordinates. So again, realize that this is a calculus course, and since we're dealing with measurements of small things, it's also differential calculus. And so the types of things we'd be interested in are lengths, areas, and volumes. So differential length is a vector, and it can be represented in different forms. This is ds. It could also be represented dl in bold in 2D and in 3D. A differential area, well, in 2D, basically, we'll usually use the symbol dA to represent a differential area. But once you're looking at curved surfaces in 3D, then that's an oriented differential area, in which case we'll use a vector, a d, uppercase S, to represent the fact that it is a differential area and it's a vector in 3D. And finally, differential volume, which is a scalar, and we'll represent it by a dV, and that's, of course, in 3D. So this table basically shows you, for instance, in Cartesian 2D, 3D, polar coordinates, which is 2D, cylindrical, which is 3D, and spherical, 3D. And so ds, basically, these are the expressions in the various coordinate systems for measuring length, a differential length. This is basically dA. And so, for instance, you'll notice here in Cartesian 3D, this has no relevance. However, in 2D, which would be Cartesian, then dA is dx dy, whereas in polar coordinates this would be r dr d theta. And for as far as the differential surface area is concerned, we don't normally use this in Cartesian 2D or polar 2D, because in 2D there is no orientation, it's just in the plane. However, in 3D, particular coordinate systems we're concerned with, which is Cartesian, cylindrical, and spherical, then we do have an oriented area. In 3D, there are three principal planes, the dxy, dyz, and dzx. And because they're oriented, they're basically normal to the plane, so z hat, x hat, y hat. And you can see this is basically ds subscript z, representing the component that's basically sort of a vector pointing in the z hat direction. If you look at cylindrical, you'll notice that in this case, the coordinates are typically r, theta, and z. And so you can see the r here corresponds to the r hat, the theta corresponds to theta hat, and the z corresponds to z hat. So this would be the magnitude of the differential area associated basically with the r hat direction. This is for the theta hat, and this is z hat. Similarly, for spherical coordinates, you can essentially show that the differential surface area with respect to the rho hat direction takes on this form. For phi hat takes on this form, and for theta hat takes on this form. And lastly, for differential volume, for Cartesian coordinates, it's just dz dy dx, or an iterated version of that. In cylindrical coordinates, this becomes r dr d theta dz, and in spherical coordinates, this just becomes rho squared d rho sine phi d theta. All right, so that concludes lecture 25C. Thank you for listening.